Hi, good afternoon. Okay, so hello everybody. Today is our last class, um, except for two more classes on Monday and Tuesday. Now on Monday and Tuesday, again, I don't think so many of you will show up. I think, well, not many of you have shown up in recent classes anyway. So, the point is that I will be using those two classes to do course revision and also to solve numericals and to answer any doubts that people might have. Okay. So from that perspective, if you want to have your questions answered, if you want to see some numericals being solved, etc., I would suggest that you show up on Monday and Tuesday. And then there is one homework assignment. I will upload that today. And of course, my expectation is that all of you will try to do the homework assignment on your own before turning to help towards your other students. And then there's a quiz on March 30th, which is on this quantum mechanics portion. Again, don't take too much tension about the quiz. Remember to focus on the basics, the fundamentals. What is the wave function? What is probability? On wave particle duality, and your concepts from the Davison Journal, Stern-Gerlach. Well, Stern-Gerlach we didn't really cover in class, so never mind. Photoelectric effect, black body radiation. In black body radiation, there is a bit of a calculation. You don't need to worry about the details of that calculation. The important thing is to just keep the qualitative description in mind. And again, the last thing I want any of you to do is to resort to any kind of rote memorization or rectification, as we say. Because as a student growing up in India, the biggest, I found that the biggest enemy of any kind of creative thinking is this habit of rectification. Unfortunately, due to factors beyond my control, I do have to cover a certain amount of syllabus with you. But my effort, I try my very best to make sure that I can cover it in a way that doesn't require you to memorize things, but rather to understand things. Whether I'm successful or not in that, I don't know. So, all right, so let's start by just going over what we have done so far. Right? So we started with the single particle in a box, and like I've already explained in the previous two classes what a box is and so on and so forth. And then I've already explained what a box is and so on. So we are solving this linear second order differential equation in two regions. Well, there are three regions, but two of them are the same, right? So now the solutions are very simple. The solutions are in both those regions. In one region, you get in region 2, that is, you find that the solution is cosine and sine. And since it's a linear second order, it's a second order differential equation. So you have two linearly independent solutions. So your general solution, phi of x, will be a linear combination of those two solutions. And linearly independent means that one solution is not a scalar multiple of another, right? So cosine cannot be written as some multiple of sine. Now, then in the regions 1 and 3 outside the box, you have the same kind of solution, but now there's a very important difference, which is that this k prime, the value of this parameter k prime, it depends on whether your energy is equal to, greater than, or less than your potential. So if your energy is greater than the potential, then k prime is a positive. And again, you get plane waves, you get cosine and sine. But if the energy is less than the potential, so in that case, k prime will become complex, it will become imaginary. Now, there are two ways to deal with this. One way is that you can put an imaginary k prime directly into the solution, right? And you can use the fact that if you take the cosine or the sine of a purely imaginary number, it can be written as a sum of complex exponentials, e to the ix plus e to the minus ix. So, sorry, no, as a sum of real exponentials, e to the plus x, e to the minus x. The other option is to write ek prime as v naught minus e to switch the sign. And so this way k prime becomes a positive number, right? So this becomes a positive number. And when this becomes a positive number, then our differential equation can be written as in this way, right? Where our negative sign is no longer present, right? So in the earlier version, there was a negative sign, but here there is no negative sign, right? So now your solution cannot be cosine and sine because of the different sign, right? So your solutions will be of the form real exponential, right? Exponent plus minus kx. And you can also write the as cosine and sine, but again, cosine, hyperbolic cosine and hyperbolic sine. But again, hyperbolic cosine and sine are linear combinations of these exponential functions, right? So now in regions 1 and 3, we get two branches. One is an exponentially increasing branch and one is a decaying branch. And these branches are indicated here. For region 1, these branches are indicated by this line and by this line. And the requirement that the wave function, this quantity, right, when we take the square of this quantity and we integrate that quantity, we should get a finite number, because the square of this quantity is the probability density, and the probability density should add up to 1 when you sum it over the entire region. So if you look at what happens with the exponentially decaying branch, as you go to negative infinity, like in the x direction, the area under this curve becomes infinitely large. So we have to throw away this branch. It's not physically, it's not allowed. And so in region 1, we can keep only the exponentially increasing branch. Now, you might be thinking that, well, it is exponentially increasing. Isn't that a problem? Well, it's exponentially increasing only up till the boundary of the potential well, right? Only up to x is equal to 0. After that, the oscillating solution takes over, right? So this function is well defined and it's finite in the whole region from x is equal to minus infinity to 0. There is no problem. Similarly, in region 3, by the same logic, we will get two branches, right? We will get exponentially decaying and an exponentially increasing branch. In this case, we have to take the e to the minus kx branch. Okay. And so finally, we can write down the complete solution for our particle in a box. In region 1, the solution is, we can write it as c times e to the k prime x. So this is for x is less than 0. In region 3, it's some quantity. So now d, c and d, these are all constants, right? So you can always have a constant multiplier. This is for x is greater than L. And then at region 4, sorry, not region 4, in region 2, that is in between in the potential well, your solution looks like this: cosine k prime x plus p sine k prime. So this is for, okay. This is the complete solution for the particle in a box. Well, it's not complete yet because there are several things that are missing, right? We don't know what these constants are, what this A, B, C, D is. And also we don't know what K prime can be. So the question is, what are A, B, C, D, and can K prime take on any value in R or only some subset of R, right? So to do this, to solve this problem now, we will take the limit of an infinite potential. So up till now, our well is not an infinite well, right? We have taken V0 to be a finite number. Now we will take the limit that V0 goes to infinity. Now, when we take the limit that V0 goes to infinity, what happens to these two expressions, right? So let's look at the solution in region 1. The solution in region 1 is c times e to the k prime x. Now, you have to keep in mind that in region 1, x is less than 0, right? So x is less than 0, which means the exponent, right, is negative, right? So this is exponent k prime x, right? But since x is always less than 0, the exponent is negative. Now, what happens when we take the limit V0 goes to infinity? So k prime is equal to 2m V0 minus e by h bar square, right? So if you take limit V0 goes to infinity, then what happens to k prime? K prime also goes to infinity, right? Now, I have an exponential function, okay? And let me write it like this, minus k prime x. If I take limit k prime goes to infinity, what happens to this exponential? Or let me write it as plus x, and let me say for x is less than 0. What do I get on the right hand side?
Zero.
You get 0, right? Because the exponent goes to negative infinity, so this goes to 0. So what this, and this is true for all values of x, right? So this implies that what happens to the wave function? The wave function goes to 0 in region 1. Okay, and this makes sense. Again, you have to remember that we are doing physics. So whenever you solve a problem, you should always ask, do the solutions make sense based on, do they make physical sense, right? So, well, remember what is phi x, right? What is phi x, right? Well, phi x squared is the probability density, right? So phi x squared dx is what? It's the probability of finding the particle between x and x plus dx. This is the, so phi x square is telling you what is the likelihood that if you open the box and look at the box, or you look at the system and you see that the particle is in some location, what is the probability of finding the particle in that location, right? Now, let us look at what this picture is telling us now. Okay. This picture is telling us that as I go towards the left, towards minus infinity, right? As I go outside the box, right? So this region 2 is inside the box. Region 1 is outside the box and region 3 is outside the box. So what is happening to the probability of finding the particle? You can see that as I go to x from 0, as I go to the left, from x is equal to 0, what happens to the probability? P of x goes to 0, right? It declines. That means I have some probability of finding the particle outside the box, but as I go outside the box to further and further regions, that probability becomes less and less, right? Similarly, if you go right towards positive values of x, from x is equal to L, what happens to the probability? Again, the probability goes to 0, right? Now this is a box. If you put something in a box, what should be the probability of finding the particle outside the box? So that sounds like a very simple question, right? I have a box, I put something inside the box. What is the probability of finding it outside the box?
Zero.
Zero,
Zero, zero.
right? But what quantum mechanics is telling me is that the probability of finding the particle outside the box is not zero. It's small, but it is not zero, right? And this kind of makes sense because, well, I mean, it doesn't make sense intuitively, but I mean, if you think about it, if you imagine that you are in a box, right? This is the box, and you are trapped inside this box. Okay. Then what is the probability that you will be outside the box? Well, classically, you will say that the probability for outside is zero, right? But classically, the assumption is that you will never have the energy to break through the wall, right? You don't have that superpower. You're not Iron Fist. So imagine that you have that superpower and you can punch and break the wall. Now, what will happen? The probability of finding you outside the box will no longer be zero, right? You can break your way through the wall, right? But now let me make the wall, let me make it I'll make it thicker. All right. So I'll put one more layer. I'll be like, yeah, this guy is very hard to keep inside the box. Let me make the wall a little bit thicker. Right. Now what will happen? Now what will happen is that, well, you could still punch your way through the second layer, right? But the probability of you being able to do that, the chances of you being able to do that will be less, right? So as you keep increasing the thickness, the thickness of this wall, what happens? The probability of you being able to escape outside goes to zero, right? Now, in our case, the thickness of this wall, right? This thickness, this is like the height of the potential barrier V0. So when you take V0 to infinity, it means that the person inside can never punch their way outside, right? And so if you take V0 to infinity, now I'll draw the potential well like this, but it's understood that this is infinite. Okay, so the top of the well is like at infinity. Okay, so I don't really know where the top is. This is just a schematic drawing. All I know is where the bottom of the well is. Okay, all I know is that where is the bottom, right? So now what can I say about the state? Yes, Lavanya, is there a question? Lavanya, is there a question? Okay, I guess maybe you typed in the wrong box. Okay, so now what happens to phi of x? Remember that phi of x goes to zero, right? In this region outside the box. Okay. And what happens to phi of x inside the box? Well, inside the box,
tending to
it has an, sorry. Go ahead, you what?
sir, I told it will
Chris?
be it will be like tending to one, I told sir.
Tending to
Probably.
1, well, it will be oscillating, right? It has some oscillatory behavior inside, right?
Yes, sir.
Right. Now, so now we can look at the solution in region 2, that is inside the box. And remember that the solution looks like this: A cosine kx plus B sine kx. Okay. And what is the location of the box? It is between x is equal to 0 and x is equal to L. Right. And now, if you take limit x goes to 0 from the left hand side, so negative, that means you're coming from the negative, right? What is the value of phi of x? It's 0, right? Because coming from the left hand side, you're taking this side of the function. Now, this function phi of x should be continuous. Okay, so continuity means that if I take the limit of phi of x to 0 from the right hand side, I should get the same answer. Okay, so let me write it like this: phi of 1 x at x is equal to 0 is 0, right? Phi of 2 at x at x is equal to 0 is equal to what? Well, this term will just give me 0, right? Sine kx is equal to 0 because x is 0. And this term will give me, what will it give me? It will give me a.
A.
Because cosine of 0 is 1. Similarly, phi of region 3 at x is equal to L is equal to 0. So phi of region 2 at x is equal to L. Now what is this? This is equal to A cosine KL plus B sine KL. Right?
Yes, sir.
Okay. So this condition, right? This is the continuity condition. There are two conditions. These two continuity conditions tell us that the first one tells us that A has to be equal to 0. Right? Otherwise, this condition will not be true. Right? The second condition, and I'll write it like this so that it reads a little bit better. The second condition, and again, the second condition tells us that now A is 0. From the first condition, we have that A is equal to 0. So the second condition tells us that B times sine KL is equal to 0. Right? Because this value has to match this value, and it should be B2, phi 2. Okay, so these are called boundary conditions, by the way. Okay. So we can call this boundary condition B1 and we can call this boundary condition B2. So these two boundary conditions together, they tell us that the solution inside region 2 is given by B times sine kx. Okay. And now you remember from this condition, B sine kl is equal to 0. So first let's look at this, right? So we have B times sine kl is equal to 0. What does this tell us about the value of kl?
It will be n pi, sir. Value
Kl
of,
has to be equal to n pi, right?
yes, sir.
So k has to be equal to n pi by l. And what is n? N is any positive integer,
Integer.
right? 1, 2, 3. Positive integer. Well, you can have negative integers also, but you get the same. Well, yeah, you'll get the same answer. The sign of phi doesn't matter, right? At the end of the day, remember that we look at probability. Probability is obtained by taking the square of phi. So if you take a negative integer here, you'll get sine of minus n something. So the wave function will become negative. But the probability will be the same, right? Because you take the square. So we only take the positive integers. So our finally what we end up with is phi of x is equal to 0 for x is less than 0 and x is greater than L, and it's equal to B times sine, okay, and what is k? K is n pi by L times x. This is our solution for a particle in a box, for a particle in an infinite potential value.
Sir, should we memorize this one, sir?
Good one, Sukrit. I don't really know what to tell you, man. Right. I don't really know what to tell you. What you should know is the procedure. If you know the procedure, then you can derive it. Right. Again, memorizing it is not going to help you understand where the different parts come from, right? Why is this n pi x over L? Memorizing is not going to help you understand that, right?
Yes, sir. But yes, sir.
I mean, what learning strategy you want to adopt is your choice, right? I don't want to tell you how to study. Now, we still don't know what the value of B is. Okay. So now we will use the property of normalization of probability. Okay. So what is normalization? Normalization means that if I take Px and I integrate from minus infinity to infinity, I should get 1. So in other words, the integral from minus infinity to infinity of phi of x squared dx is equal to 1. Right? Now this integral has 3 portions. This integral can be written as an integral from minus infinity to 0 of phi x squared, and integral from x is equal to 0 to x is equal to L of phi x square, and integral from L is x is equal to L to x is equal to infinity of phi x square, right? But since phi x is equal to 0 in these two regions, these two integrals are 0, right?
Yes,
Because
sir.
phi x is 0 in both those regions. So finally, we are left with the condition that x is equal to 0 and phi x is equal to 1. Okay, I guess we got disconnected there for a second. Am I audible now? Can somebody please confirm?
Yes, sir, you're audible.
Okay. So we finally we have this requirement that the integral of phi of x square from 0 to L should be 1. And this means that the integral of b square sine square n pi x by L has to be equal to 1. Okay. So b square is a constant, right?
Yes, sir.
So we can just we can write this as b square integral of x is equal to 0 to L sine square n pi x square. So now the question becomes, what is the integral of sine square? Okay.
We should convert it to cos 2x.
Sukrit, I'll ask you when I ask a question, then you can let me know the answer. Okay. Thanks. So one way to do it is to note that if you take sine square n pi x by L plus cosine square n pi x by L, right, from 0 to L, the integral of this quantity will be 1. So this is equal to 1. This is identically 1. So the integral of this quantity is going to be L, right? And since between 0 and L, you will always get an integer number of half ratios which fit between 0 and L. So we can say that this will contribute to one half of the integral and this will contribute to the other half. And so we can write down integral of 0 to L sine square n pi x over L dx is going to be equal to L by 2. Okay. And again, exercise, check this explicitly by, as Sukrit was saying, writing this sine square in terms of using an identity 1 minus cosine 2. So you can write sine square x is equal to 1 minus cosine 2x, right? If I'm not mistaken.
Divided by 2, sir.
Thank you. Divided by 2. So I am mistaken. So please check this explicitly by making the substitution and doing this integral. Okay. So finally, what we have is that the integral of this quantity. So we have that integral of phi of x square dx from 0 to L is equal to b square integral of sine square n pi x over L dx. That's equal to b square times L by 2. And then my requirement is that this is equal to 1 by normalization. So this tells me that b is equal to root 2 by n. And so my solution becomes pi of x is equal to root 2 by L sine n pi x over L. N is a positive integer. Okay. Now let me try to find a nice applet which can illustrate these. Okay, well, maybe I'll just show you the plots myself. So I will show you these plots in the software package that I've used before called GeoGebra, right? All right. So our box is defined as between x is equal to 0 and x is equal to L. Okay. So we will take our parameter L. We can set it to whatever we like. Let's take L is equal to 10. All right. Now, so our equations, our solutions go as root 2 by L. All right. So let me write that as b is equal to square root of 2 by L. Okay. This is b. Now, what are my solutions? Let me write down the first solution. Okay. f1x. f1x will be equal to b times sine n is equal to 1, remember, or actually even better, let me write it as n is equal to 1 as an integer like this, and then I can write fnx is equal to b times sine n and then pi x divided by L.
L.
Okay. And let's see settings. Okay, so we are not interested in what happens outside L, outside 0 and L. Okay, you can see what is happening between 0 and L. All right. And now what I'm going to do is actually I'm going to take this b and multiply by a factor of 10. I'm doing that just so that the function is clearly visible. Okay. So between 0 and 10, this is the first state. Okay, this is the first state. Now, what about the second state? Okay, so the second state corresponds to n is equal to 2, right? So let me change this. Slider increment is 1, 10. So let me change it to n is equal to 2. Now what happens? You can see, right, that our function changes. So in the first case, there is one maximum. So actually, it's better to just draw b sine 2 pi x by L, b sine 3 pi. Okay. And so these are my first three solutions. This is called the ground state. This has the lowest energy. This is my first excited state. Okay. And this is the third state. Now you can see that each time as I increase the level n, right, I'm increasing the number of oscillations that are present in the solution, right? So if I go to B, if I go to this thing, n is equal to 4, right? You will see 1, 2, 3, and 4. Four peaks and troughs, right? Now, what are these? These are basically standing waves, right? What is a standing wave? A standing wave is that when you take a box and you set up an oscillation inside a box, then at the walls of the box, the wave cannot oscillate, right? Because, well, you have a wall over there, right? There's nothing to oscillate. So the wave cannot oscillate at the walls. So at the walls, there should be an antinode. Sorry, there should be a node, right? So that's what we have. Node means there is no oscillation. That is at x is equal to 0 and at x is equal to 10, right? And then we ask how many waves are there which can fit inside this box, right? And so you end up with the condition that the wavelength lambda by 2 has to be the length of the box L has to be an integer multiple of the wavelength divided by 1/2. So you get L is equal to n lambda by 2. And that is exactly the same condition that we have here. So these are the standing waves. This is the first standing wave. This is the first standing wave, then the second standing wave, then the third standing wave, and so on. Okay. Now, what about so what about the probability, right? Remember that the probability of finding a particle is given by the square of the function, right? So now if I look at the first excited state, that is n is equal to 2, this is the state. Okay. Now you can see that what happens to the function phi. The phi is positive in this region, but here it becomes negative, right? But if I take the square of this quantity, the square is positive everywhere, right? So this represents the probability of finding the particle. Okay. So let me do the same thing. So this is for n is equal to 1. For n is equal to 1, the green line represents the wave function and the orange line represents the probability which is obtained by. Then this is for n is equal to 2. Again, phi becomes negative, but phi square always remains positive. For n is equal to 3 and so on. You can see that the same pattern is occurring, right? So this is what the solutions look like for a particle in a box. Now,
Excuse me, sir.
yes.
Sir, like, if you don't mind, can you remove the value of 4 from the value of B, sir? Like, you have multiplied the value of 4 to B.
Well, that is purely for ease of viewing.
Yeah, yes, sir. Yes,
right?
sir. I can understand. Like, if you don't
Okay.
mind, can you, like,
Well, I've already done my. Oh, sorry about this. I'm already finished with that part. You can feel you're free to play around with that.
oh, fine, sir,
Yeah,
fine.
yeah. It's not going to make any difference at the end of the day. So our solutions look like this. This is x equal to 0, x is equal to L. This is the first excited. This is the first state, which we call the ground state. Then this is the first excited state. Okay, and this one is something like this. This is, so you get n is equal to 1, n is equal to 2, n is equal to 3. And each time what you can see is, what is happening? The wavelength is becoming less. As n increases, lambda decreases, right? And as the wavelength decreases, what happens to the momentum of the particle? The momentum increases, right? So each time, what does n represent? So n represents the energy of the particle. Okay. N is equal to 1 is the ground state. And this ground state is the lowest possible energy. So the lowest possible energy of the particle. And this lowest possible energy is not equal to 0. Why is it not equal to 0? Well, that has to do with the uncertainty principle. And well, I haven't really talked much about the uncertainty principle, and I think it would be too much for this class to continue talking about that today. So maybe I'll have an extra class tomorrow in which I can talk about that uncertainty principle. Okay. But I'll stop here for now. Okay.
Okay, sir.
Yeah. Questions?
Sir, we proved that proved the value of we took the function phi x is a cos omega like kx plus v sin kx, no, sir. After
In
getting
which one?
a today proof, sir. After getting a is equal to 0, how did we get that K, sir. Like,
how did we get at K, right? We looked at the value of phi at x is equal to L. So we got A is equal to 0 by looking at x is equal to 0.
yes, sir. A is equal to 0. After that, sir. What do we do?
So then we look at x is equal to L. What happens at the other boundary? There are two boundaries, right?
Yes, sir.
So at that boundary, again, we have to have that the state phi 2 at x is equal to L has to equal phi 3 at x is equal to L.
Yes, sir.
Right? And phi 3 at x is equal to L is 0 coming from the outside.
Yes, sir.
And phi 2 is what?
Okay.
It's equal to this
P
statement.
and K. And that we equated to 0. Got it, sir.
And this is already 0.
Yes, sir.
So you have that B sine KL is equal to 0.
Yes, sir.
That's how we got this. Now, another thing to keep in mind is that, remember, we can shift our potential any direction we want. Okay, it doesn't have to be at x is equal to 0 and x is equal to L. Right? So what happens if I shift my potential from, let's say I go from x is equal to 0 L, instead of this interval, I go to x is equal to minus L by 2, L by 2, right? So to go from here to here, what is this? This is taking x, the argument of that function, and shifting it by minus, subtracting L by 2, right? So this is a coordinate change of minus L by 2, right? So what will happen to my state, phi of x? Phi of x is root 2 by L sine n pi x over L. So now if x goes to x minus L by 2, then phi x will go to root 2 by L sine n pi by L x minus L by 2, right? And this will be equal to root 2 by L sine n pi x over L and minus n pi by 2, right? So now what is this equal to? What happens to this function? So when n is equal to 1, I get sine of something, sine of something times x minus pi by 2, right? And what is that equal to? That is equal to cosine, right? So if you look at this function, sine n pi x by L minus n pi by 2, what is this function become? For n is equal to 1, okay. For n is equal to 1, this function becomes sine of pi x over L minus pi by 2, right? And I can write that as cosine pi x by L. For n is equal to 2, it becomes sine 2 pi x by L minus pi, right? What is that equal to? That is equal to sine of 2 pi x by L, right? Similarly, for 3, what will I get? I'll get cosine 3 pi x by L and then sine 4 pi x by L and so on. So the form of the function, it depends on the location of your of the edges of your potential well. Okay, so if you have x between L and 0, then what are the solutions? The solutions are of the form sine n pi x over L. But if your solution is between, let's say, L by 2 and minus L by 2, then our solutions are of the form cosine n pi x by L for n odd number, for odd n, and sine n pi x over L for even n. So sometimes you will see the solution given for this kind of a potential, but it's exactly the same potential. Remember this. If you look at the shape of these functions, nothing changes. The only thing is that because you're shifting the coordinates, you have to change the you have to change the expression, right? But the function remains the same, right? So if I look at the ground state looks like this. This is sine. If I shift it from minus L by 2 to from this to this, what happens? It looks like this, right? Now this function is what? This function is sine pi x by L. And this function is cosine pi x by L, right? But they are identical in every way, right? They have exactly the same property. It is just a question of what you define as your origin, that's all. Okay? All right. Okay, so I guess that's enough for one day. Are there any questions? Any other questions? Okay. All right, then. Yeah, we'll probably need to have an extra class tomorrow. So let's plan for that, okay?
Thank you, sir.
All right.